really didn't know that I had my audio off, but
Oh,
I said
gotcha.
I've been working the past couple of days a lot, so I haven't really had the chance to go through all of it. I got a lot of the stuff screenshotted for the
Okay.
retake of the test, so I'm just gonna look through and see which ones I kind of got wrong.
Yeah, and don't like yesterday, remember, or day before yesterday when you were with me in our class, we did find that one of them actually had an error. So, just remember that occasionally happens. I don't
Yeah.
recall any more other than that. I'm not trying to hint to you that other ones have mistakes. I'm just saying there is a possibility. So, if you really think you got the right answer and it's not the one that it's showing, let me know and I'll let you know if it's right or wrong.
Okay.
So, but this is just a free question answer session where y'all can, ask me any questions you might have from the old tests, from the old online tests, from the practice tests. Homeworks aren't that important. I mean, they're important that you do them throughout the semester, but they're not that important as far as preparing for this final. So, if you have any of those questions, I'll certainly answer them. But you're not, well, assuming I can. There's sometimes you just, I get to draw a blank or something. But generally, yeah, I can answer those. It's just those are probably not the most fruitful ones for preparing for the final. And I
Okay.
see Joseph is here. So, Joseph, feel free to ask any questions. You just speak right out, or you can even send a message in chat if you'd like. Let me know if y'all have any issues as far as your name appearing on the internet. I know not everybody's done this before, like my internet students, but this does go on the internet on my YouTube channel, which it has a whopping 300 subscribers. Uh, but honestly, it's probably only three that actively look at it. So if you're scared of being outed by three or four people worldwide, let me know and I'll make sure I get rid of your names on everything.
I just had a quick question about the scheduling for the final exam, actually.
Okay.
So I saw that you had mentioned that you were going to talk to Professor Johnson about like the labs or scheduling for like during the lab time, but our lab time was like 7 o'clock on a Thursday night. So I was wondering, like, is that still an appropriate time to take that, or?
That would have been, but I still haven't heard back from Dr. Johnson. It's Johnson, right?
Yes, yeah.
Yeah, I still haven't heard. I'm checking my email right now just to double check, say if I haven't missed anything. But in his defense, he really had he probably had no idea about this. I'm not sure that when we hired him because I wasn't in the hiring process with
Ah,
this one because I stepped down as chair. But I'm not sure that he was even explained that that's normally what we do with the lab. So he might be literally already gone for the semester or something. I don't know.
okay.
But still nothing from him that I see. No.
As for like you offered a bunch of times for like taking it, would I just like go to the testing center or would I go to like a office of yours?
Yeah, so those times that I gave you are times where you'd actually come to me and
Okay.
you'd be in one of my labs like JC21, JC26, or JC28,
Okay.
or maybe even in one of the classrooms, but I'd be on that JC hall.
Got it. JC 26 or JC 28, you said?
Uh-huh.
Okay. I'll take note of that. And should I send you an email once I find out what time I'm going to be coming in for the final exam?
Uh, yeah, if you once you actually know, that would be nice, but I don't require it. Like I
Okay.
don't need to know if you're planning on attending one session or the other. Just as long as I know you're going to take it, that's golden.
Got it.
Uh, no, he has not replied. I just double checked and my email's there, but without a response yet. So
Okay.
so yeah, that you're still free to take it at the testing center anytime they can accommodate you. I'm gonna submit a uh proctor request for the testing center, and they expect that for the internet classes. So
Yeah.
I'll be doing that over the weekend. But I sort of had to decide the format of the test and everything before I can do it. That's why I haven't submitted it yet.
Yeah, I'm glad to hear you're feeling a little bit better. That's good.
Thank you. I appreciate that. I do feel a lot better. I still don't have any idea if I did the deed or whatever, but I feel a little better. So yay.
Okay, well that was all the questions I had to know. I just want to know about the schedule in there. So thank you very much for answering those. I appreciate it.
You're welcome. Feel free to come back if you have any questions. I got another one tomorrow.
Okay,
Uh,
sounds good.
all right.
Have
See
a
you,
good one,
Joseph.
Professor.
How about you, Kyle? You got anything, bud?
All right. I'm just kind of looking through some of these real quick.
No problem. No rush. I'm just gonna sit here and look pretty because I'm such a handsome dude.
Okay. Uh,
I can't help it. It's just how awesome I am. I'm just looking at my hair like I just got up, and it's funny, but even with short hair, it can get like matted and flat down and stuff. My mom says it
Yeah,
looks like newborn hair.
mine looks like I get electrocuted.
That's great. That's the way my daughter's always was. Man, she can fall asleep for like 3 seconds, and like her hair will be
Poof. Yeah, I mean, mine just goes. My sister has the same hair. Hers comes down to like past her shoulders.
right.
If she brushes it when it's dry, it'll come out to her shoulders. It'll be like
Oh God.
a fucking 2 feet wide.
That's great. Hey, Vanessa,
Hi.
feel free to ask any questions. It's just an open session for you to ask questions. I'd normally go through one by one and ask a question, but nobody has any questions yet. So right now, I'm just asking for everybody to ask questions.
So when it asks how many electrons are necessary to produce 1 coulomb of negative charge,
Hmm.
so wouldn't that be 1 over 1.6 times 10 to the negative 19th, which would make it 1.6 times 10 to the 19th?
It'd be 1 over parentheses 1.6 times 10 to the negative 19, and 1 over 1.6 is not 1.6. That's the only problem. 1 divided by 1.6 is equal to 0.625. Wow, that's crazy. I didn't know my calculator could do that. So it'd be like 0.625 times 10 to the 19th, which would be, 6.25 times 10 to the 18th or something. But yeah,
Okay.
your thinking's exactly right. More generally, Kyle, and this hopefully will help for everybody that sees this. What I try to think about when I'm doing those types of what modern students are calling story problems, what we used to call word problems. I try to teach this because it was like a discovery I made later on in life about how to work through it. But you can imagine having 1 coulomb of charge, just some picture of what a coulomb is, and then you can pull out one electron or one negative coulomb of charge. You can pull out one electron, and then you'd have left 1 minus 1.602 times 10 to the negative 19th. And then you pull out another one, and that would be 1 minus 2 times 1.602 times 10 to the negative 19th, and pull out another one, and you keep subtracting out electrons until you get up to the negative 1.0 coulomb charge. When you do that, whenever you're repeatedly subtracting, pulling something out, that means
Yeah.
divide. Similarly, if you ever do the other thing, like you're saying one, okay, I need to add this to it. All right, I need to add this to it. Repeated addition means multiply. So it's always a neat little thing to do that. But if you could picture the thing like the coulomb, the negative coulomb, as an
Yeah.
object, and you just pull out little bits of charge at increments of e, that's multiple subtraction, and repeated subtraction is the definition of division. So hopefully that's some information that might help you. If it's too abstract, don't even mess with it. But
Yeah, that
uh,
sounds too complicated for me. I just know I just need to divide it. And I
yeah,
just looked at it as like a 1 over 1 instead of actually dividing 1 divided by 1.6. I'm like, oh, just bring it up to the top is what I thought. And that's what
exactly.
got me.
That's just a being good at math, but having forgotten little details that you occasionally
Yeah.
make mistakes with, like we all do. Good deal. Uh, Brittany, did you have a question?
Uh-oh. No, I'm just here to listen to
Oh, I
see
see
if
that.
anyone bring up the same questions I might have.
No problem. I just saw your message to that. Sorry about that, Brittany. And Vanessa and Kyle, like I said, if you come up with anything, just let me know. Uh, I don't really have much. I don't prepare for these things other than, just making sure I know the material, but I don't prepare for them in that, like I don't prepare lectures or anything because I know
Right.
nobody wants to do that.
Can we go over some of the conceptual questions? Maybe not so much the math right now but like,
Absolutely.
uh,
That would be a good
over,
idea.
okay, over ordinary temperature ranges, the resistance of most metals, such as copper, I thought it decreased as it gets hotter.
The resistance gets larger as it gets hot for most metals. And the reason why is remember that average random kinetic energy that atoms and molecules and particles have as a result of temperature? when that goes up, it's sort of like not only are you now trying to get elderly people out of an old folks home through a hallway, like we talked about when we did the R equals rho L over A formula, but now you've got a bunch of young kids playing, hide and seek or something in your way, or crash, or slam dancing or something in your way. So the more active the active molecules and free electrons and stuff like that, the more fast they're moving due to high temperatures, the harder it is to get down that hall. So that's why the resistance generally goes up with increasing temperature.
So just because the more active the molecules are, the harder it is for them to go down a wire.
Yeah, and it's really more. It's as far as I can tell, it's partly the molecules, but I think it's mostly the motion of the electrons having their random motion, kind of getting things in the way.
Okay.
I did have a question too about the concepts for like the magnetic field on a magnet bar, right?
All
So
right.
I think I remember in class you mentioning that the south is technically like where most of the protons are, the north is the electrons, if I'm
I didn't say that intentionally, but I might have by mistake. But
okay.
there is a line just like that that would be easily misinterpreted that way. When
Mm-hmm.
when the charged particles come from our sun, that's called the solar wind. Uh, they interface with the magnetic field, or they run into the magnetic field around the Earth. And when that happens, what we know is the force on charged particles is QVB sine theta,
Mm-hmm.
and the QV makes a vector and the B makes a vector, and the force is a third vector that's perpendicular to both QV and B. So what that means is you can only cause these charged particles to turn left or turn right or turn up or turn down. Well, if they're positive, then they're going to turn one direction. If they're negative, they're going to turn the other direction. But the way that works out is you can still have both positive and negative particles going to the north for the aurora borealis, and you can still have positive and negative particles going to the south. It's just they would probably, like, the positive particles might spiral this way going to the
Mm-hmm.
North Pole, whereas the negative particles would spiral that way going to the North Pole.
Yeah, because I noticed on a conceptual question, it does ask about like if a proton or an electron is entering a magnetic field, right?
Mhm.
So like, I mean, I got this one right. I'm gonna be honest, I'm not sure exactly. Like, I don't think I really fully grasp it. But like, question 18 says an electron is moving to the right as shown in the figure. Suddenly it encounters a uniform magnetic field pointing out of the page, which of, or you know what? That's not the one I was confused about. It was
That is a good one,
17.
though. Come back to that. That would be a good one
Yeah,
for me to
because
demonstrate.
I mean, pointing out of the page, I know the right hand rule is what helped me got that question right.
Right.
So, but for 17, on the other hand, it says like a proton moving west enters a magnetic field. Because of this magnetic field, the proton curves upward. We may conclude that the magnetic field must have a component. I knew to put towards the south because again, my thinking was, you know, I'm guessing if the proton is moving upward, that's a sign that it's being attracted to the negative of the magnetic field, which is the north, right? So I just
Okay.
wanted to be sure that my understanding was correct.
Okay, let me explain how I would explain it, and what wording you have might not be correct, but that also
Hmm.
might not matter if you understand what you're talking about.
Hmm.
I will restate it in my own words, using
Okay.
my own way, and if that seems consistent with you, go for it. You don't have to change your words. Sometimes your words aren't, you meaning any humans, words aren't exactly correct, but in your mind, if you're thinking it and it gets you the right answer, then go for it. So
Right.
the way this works is the and this is the whole reason I brought up vectors at all with the F equals QVB sine theta formula. The QV is one vector. And what that means is it's either parallel to V if you got a positive charge, or it's in the opposite direction of V, which is anti-parallel if you've got a negative charge. You're talking about, in this case, an actual positive charge, and you said it was going to the west, right?
It said that it curved upward. It's a proton curving upward once it hits the magnetic field. So my thinking was it was going towards the negative part of the magnetic field.
Yeah, that those words sound a little confused to me. But the part before that, did it say the proton was moving to the west or?
Oh yeah, it did. I'm sorry.
Okay,
Yeah.
so let's imagine. I know right now I'm looking in this house. Roughly north is that way, but I'm going to pretend north is this way. So north is this way, east is this way, west is this way. So our positive particle is going this way, and since it's positive, QV is going this way. And what we want is a force that points up. Well, I use this mostly with your class, and this vector is supposed to be, or this finger is supposed to be parallel to QV. So I point my index finger to the west, which is my left. I know it's opposite for you guys, but I'm pointing it to the west. And now my hand can be in any of these positions at once until I figure out which direction B or F is. Now, this one, they didn't give you B, they gave you F. So, and this is the F here. So remember, this is QV, this is B, and this is F. They said the proton was moved upward. So that means the F should point up. And if you look, my middle finger is actually pointing towards me. So that must be a southern direction. So there should be a southern component of the magnetic field, at least to make it move upward.
Okay, but which finger is the finger that you will say will be pointing down? Is it the index, the middle, or is it the index? Like, how would you motion your hand
Okay.
to find that
I don't,
again?
there's a static one where you don't move your hand at all, and that's what I'm doing. But there is a
Okay.
one that I do where I curl my fingers. The static one was the one that I thought your class responded best to.
Yes.
But what you do is you picture a little vector Q times V pointing from my knuckle to my index finger point end, basically, and then you picture a magnetic field vector B pointing from my knuckle to
Right.
the end of that, and then this is F pointing from my knuckle up. And you got to
Right.
make sure that you think this is 90 degrees to that, and of course 90 degrees to that as well. Your middle finger can technically go all the way to just shy of 0 degrees, in other words, almost parallel, and it can
Hmm.
go almost 180 degrees, which should be just shy of anti-parallel. But if it's parallel or anti-parallel, the QVB sine theta is going to be 0, because sine of 180 or sine of 0 is 0.
So it's curving upward because of the force, correct?
Yeah, the force
Okay.
pointed up. That caused the positive particle to go up, and that's because the
Right.
magnetic field points to the south, at least partially.
Okay.
So the reason why that's a little weird is if the magnetic field has a component in the western direction, it won't affect the particle at all, and in fact, the particle will continue to move exactly the same speed in the western direction. So that's kind of weird about it.
Okay.
Uh, Noah asked a question. The final exam is open to you. So your class, Noah, meets on Mondays and Wednesdays. So you can take it on Monday at any of those times I sent in your email, or you can take it on Tuesday of any of those times I sent you in your email. So you're not allowed to do Wednesday because you're a Monday, Wednesday class, and I'm only allowing one extra day, which means you can take it as late as Tuesday. So it's completely up to you which one you take, and just check the email. I think I made times like 9:30, 10, 11, 12, and 2 or something like that on both of those days. But Noah, you can take it either of those days you want. You don't have to let me know. You just have to show up. You can take it at any of those times that I allowed for. You don't have to let me know. You just have to show up. Does that answer your question for you, Noah? It is in person, by the way. It's so if you have a computer that you can use on our Wi-Fi that runs Canvas, bring it just in case. I haven't decided whether or not it's going to be one on the computer or two, even multiple choice. It might actually be free response. There might be, a limited number like 5 or 10 or 8 questions, that kind of thing.
Real quick, the I had to run quick, but the one you were talking about, the proton moving west, it has a downward component.
Uh, no, when the proton was going west, the force was up, and that was indicative of a south pointing component of the magnetic field.
Okay,
You get that?
so that's with
is like this, because this is up, which is what the problem gave. The force is up, then that forces my magnetic field to be somewhere in between 0 degrees and 180 with my middle finger. Uh, the one that's exactly 90 degrees is due south, so that's why I chose due south.
So the direction got me screwed up there.
Yeah, so remember the formula, whether it be QV sine theta or IL B sine theta, both of those are the same. The IL, which is supposed to be parallel to the conventional current, or the QV, which is parallel to the velocity if the charge is positive, or anti-parallel to the velocity if the charge is negative. That is represented by this finger. The B is represented by this finger, and then the F is this finger. So that's all it takes.
Okay.
And Noah, I think he left, but I'm going to put it on here anyways. He said, so it is in person any of those times, no appointment. And I'm just going to say yes to him for that, just in case he checks it later. I know he dropped out, but I did shake my head at him to let him know. Did you have another conceptual question, Brittany, that you were going to talk about? You told me the proton one. Did you want to go back and look at speak about that electron one? Because that's
We can.
again good practice for all my 202 and 242 classes.
Yeah, that's fine. So that one was number 18,
Gotcha.
and it has a diagram showing path A curving up,
Okay.
path B going straight, and path C going down. And the question is, an electron is moving to the right, as shown in the figure. Suddenly, it encounters uniform magnetic field pointing out of the page. Which of the three paths shown it will follow in the field? Now, for me, I got that one right. I knew path B going straight meant it was neutral.
Hmm.
Um, and path C is going down, which was an indication, I believe, for me, like the way I interpret it was path C was an indication of an electron, because once again, I was under like the notion like of picturing a magnetic bar. And my understanding is that the positive part of the magnetic bar is the north, I think, and then the negative is the south. I don't know. I'm still trying to understand it. So like I was just kind of picturing like using that as a way, but apparently it helped me get it right.
Yeah, I think when you're saying the positive part, negative part of the magnetic field, I think you're making a connection between what you learned about electric field lines, which is
Hmm.
electric field lines. The field lines originate on positive particles and then they die on negative charges. So,
Yeah, so like cause the south goes to the north, right?
ex
In a magnetic bar.
so it's actually the mnemonic that I advise, and I'm not just trying to teach you this. I use it to remember myself. That's why I'm stating it. The
Okay.
mnemonic I use is the magnetic field is like our older population. They leave the north and enter the south. So the magnetic field line should come out of the north pole of the magnet, curl back
Mhm.
around, and then come back in the south pole of the magnet, and then they go completely through the magnet. They don't stop. The magnetic field lines are complete loops, whereas the extra
Right.
electric field lines begin on positive charges
And
and
in
end on negative
negative.
charges.
Right. Okay. All right. So I gotta try to remember that.
Okay, so on the one that you were doing, I'm going to go ahead and share my screen with my iPad for you guys so I can show you what you're talking about on this electron. So you said electron was going to the right and the magnetic field was pointing out of the page or coming towards you, in other words. I'm going to do something like that and show you how I would address that, at least in writing. So what we have is a electron moving to the right, and in my world, electrons are blue. I don't really know why, but here's the electron. Here's the velocity of the electron, like that. And then the magnetic field I'm going to make is purple. And you did say it was coming out of the screen towards us, right?
Yeah, pointing out of the page.
Okay. So that means that's a circle with a dot, a circle with a dot, a circle with a dot. And let's go. So I'm trying to show fairly uniform. So I'm trying to make it look like that. So what we now have is those are supposed to be like front of arrows, which that little dot is the sharp point that would poke you. So, so what we're going to do is we got to remember the equation is the force is equal to Q V B sine theta. This is for my 202 students. My 242 students would recognize this as a cross product. So for those students, I'll write it like this just to keep up with it. But there's also the other one, which is F is equal to I times L times B times sine theta. But you got to write it in exactly that order or it doesn't work. Uh, the reason why I'm saying all this is a vector and this is a vector and this is a vector and the same thing with this being a vector and this being a vector. Ooh, and this being a vector. Okay, so right now, what I pointed out to you is QV, that's a scalar times a vector. And if you multiply a scalar times a vector, all you do if the scalar is positive is you change the length of the vector. So if you're multiplying by a scalar that's less than 1, the vector will get shorter. If you're multiplying by a scalar that's greater than 1, it'll get longer, but the direction doesn't change. But as soon as you multiply it by a negative, which is what the electron's charge is, you flip it around. And then you do all the other stuff too. So it's less than negative, it gets smaller. If it's bigger or less than 1, it gets negative. There I go again. If it's less than 1, it gets smaller. If it's bigger than 1, it gets larger. So when I see this and it says an electron, I immediately point my index finger to the left, specifically because QV is to the left now. So QV is to the left, and then I want my middle finger to point in the direction of the magnetic field. Long as my index finger stays to the left, I can choose various magnetic field and force directions. But as soon as I choose the magnetic field pointing to me, I have to take this hand, which is like this, and turn it like that. So the middle finger is now pointed at me, and I see that the force is up. So lo and behold, yes, the force should be in the upward direction for this electron.
And that's exactly what I did. I just
Good
remember
job.
how to figure it out. I remember I took my hand to the computer screen during the test, and then I had my hand facing the direction of, well, technically the our right at the computer is really the left of the computer.
Exactly. That makes
So
it, yeah, if you get into that
right.
world, it's going to mess you up. Yeah. But
So when I had did that, I noticed that the force pointing at me was my thumb basically going up. So I chose path A. So yeah, I remember how I got that right now.
gotcha.
But I
Just
feel like
also,
that wouldn't be reliable for like other questions though.
this I think the way you're working it out, it might actually work just fine. It all depends. I would say if you try several of them and you get the right answer every time, then
Mhm.
chances are whatever you've come up with works and it works in your brain. So that's the best of all choices.
Okay, I'll
So by
try
all
that.
means, feel free with that. I'm trying to draw a diagram of a bar magnet just to make sure everybody was on the same page as to what I was saying when I said that magnetic field lines are like our aging population. They leave the north and enter the south. So what I mean by that is, for instance, this magnetic field line would do this, and I haven't drawn the directions yet, so you don't necessarily know what I'm talking about yet. But the main thing is actually go straight through just like this, and the fact that it leaves the north is just represented by an arrow pointing away from north and back along the line towards south. So that's what a magnetic field line near a bar magnet looks like. And notice it does go all the way through the bar magnet. Okay. So that's what I mean by leaving the north and entering the south, meaning like elderly people move to South Florida, basically, is what I'm saying. Anybody else have any questions? Mark, I see you here. I haven't had a chance to answer yours. Yeah. Mark, you got one, bud?
Yeah, I sent you some pictures of questions I had.
Is this an email or text message?
Text message.
Okay, yeah, I see it.
And let me look through it as well. So
Okay,
for
so I'm
question,
looking right now. You had questions 4, 5, and 6, but it looks like 5 was your focus.
oh no, I sent you a bunch of them.
Yeah, okay, so the next picture is a circuit
Yeah,
with
that's the
a,
one I want to talk about.
okay.
Question 9.
All right, so yeah, question 9. So Mark has a question from Physics 202, which, by the way, has a huge overlap with Physics 242. So actually, nobody's in here from 242. Why am I talking? So what we have here is I'm going to draw a line to just close off what I already did. So everybody know that I'm talking about something separate. What we have now is a battery. Oops, a battery of voltage V, which they might give us in the problems. Now that positive side is run to a resistor like this, and that resistor is R1 equals 10 ohms, which I'm going to assume is 2 sig figs. So I'm going to put a dot and then a bar under it, and then it's going to hang a corner, and there's another resistor. And then there's another resistor right here. This one is R4 equals 30.0. Notice I'm leaving the units off, but that's only because the symbol of a resistor is clearly good enough to indicate what the object is, so you know it should be ohms. And if it was a kilo ohm, I'd just write a K there. If it was a milli ohm, I'd write a M, so on and so forth. This one, by the way, is R2 equals 20.0. And then on the other side of this is another resistor. And this one's going to be R3
Which
equals
problem is this?
20.0. This was question, he called it question 9. Is this in a test or is this in a practice test or what, Mark?
Practice test.
This is one
Practice
of the
test
practice test
629.
questions. I think
Okay.
that was Kyle that asked that.
Yeah.
They said if 1.5 amps flows through R2, what is the EMF of the ideal battery? So with the ideal battery, they're just saying, "Hey, I didn't draw any internal resistances on this diagram, and that's on purpose because this is quote unquote an ideal battery." Okay, so what we have to do is figure out what uh, what current flows through resistance R2. So what we can do with this is we can bit by bit reduce it to a single equivalent resistance. And then what we'd have is one battery with one resistance, and that would tell us exactly what current is leaving the battery in that case. But notice that's the same current that would go through R1 and R4. And once I get that, then I can figure out all the other stuff. So the way I would go about doing this is I'd first realize that R1 and R4, in some sense, are in series, but they're separated by a battery, so we don't mess with them until afterwards, right? If R1 and R4 were both above the battery on that leg where R1 was, you could add them as two series resistors, but that's not what's going on. So we're going to leave those. But what we do see is R2 and R3 are clearly in parallel. So my solution is going to involve the formulas V equals IR, 1 over R equivalent parallel is equal to 1 over R1 plus 1 over R2 plus dot dot dot. and R equivalent in series is equal to R1 plus R2 plus dot dot dot. So that should give me everything we need. So first off, I'm going to say 1 over the equivalent of 2, 3. So the R2 and the R3, I'm going to replace that with a resistance called R23, right? And this, in fact, would be 1 over 20 plus 1 over 20, which obviously has a common denominator. So that's 2 over 20, which becomes 1 over 10. And that means R23 is equal to 10.0 ohms. So now I can redraw my circuit, and actually I'm going to keep it in green. I'm going to say now I have this battery, this resistor. Now I just have one resistor here and a resistor here as well. This is still V. This is still 10.0. This is still 30.0. And now this one has turned out to be 10.0. Now I have 3 resistors in series, so R equivalent is the equivalent resistance for the whole thing, so I don't need to call it anything other than R equivalent. That's going to be equal to 10.0 plus 10.0 plus 30.0, which equals 50.0 ohms. So now what we have is a voltage, which they never gave us, just saying it's V here. Ooh, yeah, that's a problem. Did they give us a V? I want to check that picture real quick just to make sure. I don't think they did.
No, I don't think they did as well.
Yeah, oh, that's right, because they asked for what V was. My fault. So that's okay. We're just going to carry it on. But what we know here is this circuit is exactly equivalent to a voltage V in series with a 50.0 ohm resistor, with the 0.0 not being significant. So V equals I times R gives me the voltage of the battery is equal to the current in the circuit times 50.0 ohms. Now, in principle, what we can say is this is I total, so I'll put a lowercase t on it. We'll say I total is equal to V over 50, like that. And what we're going to do is we're going to hope that somewhere along the way we can carry that symbol and everything else is going to disappear. Uh, of course, actually, we're not too terribly bad. Notice that current, by the way, is exactly what's coming out of the battery. So before it hits any resistors or anything, the total current is the same thing as the current leaving the battery and entering the battery. So that means this would be V over 50, and entering the battery would be V over 50 as well. That also means that that's what's going through the R4 and through the R1. But notice, because R2 and R3 are identical, that current is going to, in fact, decrease by exactly a factor of 1/2, because the two resistors are equal and the two voltages have to be equal. So V of the 2 is equal to V of the 3. In other words, the voltage across resistor R2 is equal to the voltage across resistor R3. And then using Ohm's law, that says I2 through R2 is equal to I3 through R3. And if you solve for that, what you'll see is I2 is equal to I3 times R3 over R2. But R3 over R2 is just equal to 1. So I3 has to equal I2. And if one current, V over 50, actually works out to be cut in half, then works out to be two separate ones that are equal to each other, then that's the very definition of cut in half. So what I would say is I2 equals I3, is equal to V over 100.0. That's because I just took the I total and divided it by 2. Now, what they said is they want to know what the voltage is for that if that current is 1.5 amps. So I'm going to set that equal to 1.5 amps. And then you can see that V is going to be 1.5 amps times 100.0 ohms. And that gives me, of course, 150 volts. Oops. My thing keeps switching to erase. So that's 150 volts. And that should be the answer. Actually, I should probably do that in a different color at least. Now I'm looking at the picture to see if that's one of the answer choices, and it appears to be yes, that's one of the answer choices. So, any questions on that one, Mark? Or
I
anybody else, even though Mark was the one that asked it?
So you did I2 equals I3 equals V over 100.
Yes. Okay. So what I did was I took this IT. Let me show what I did there. So if you look at this part right here, that's what I found the total current was, but I didn't know V. So I just left it in terms of V. But what this told me right here was that I2 is equal to I3. So that means I2 equals 1/2 I total. So if I took 1/2 of that, what I do is multiply by 1/2, and you see that that 1/2 is meaning 2 multiplied by 50 in the bottom. So that's why that became 100. Does that make any sense there? I think that was Kyle that asked that.
Kinda.
Yeah, it's not the easiest thing to conclude, but it is doable. It's just not that fun. I was trying to think of another way I could do it where we could solve for V without carrying IT symbolically like I have here, but that's pretty much seems like the way to do it, other than just realizing. Uh, I guess once we got the current down to, or once we got the circuit down to this, we could have figured it out exactly, but again, it'd be in terms of V and I. But what we know is the current through this leg right here, which is the same as the current through this leg, that leg is going to be broken in two. So we could say whatever current goes through this part, IT, means I2 is equal to IT over 2. So that's another way you can think about it. Just say, hey, I know that this current that goes through the whole circuit is the V over 1 over 50, right? That's what goes around here like this. But this isn't a real circuit. This is just a circuit that we made by reducing these two into one equivalent resistance. So the current from here to here and from here to here is the I total, but this part right here is fake because we've replaced two 20 ohm resistors with 120 with 110 ohm resistor. So what we know is in this case there's going to be a 20 and another 20, and the current has got to go equally through this one as through this one. So you can say whatever I total is going to be half as big. And again, you get the same result where it'd be V over 100 equals 1.5.
So you had to know that the ones in parallel equaled 1/2.
Yes, but you sort of know that because I've sort of been teaching you that. What we know is that when a current breaks up to go through two different parallel legs, the voltages across the parallel legs are the same. That's what we learned in lab. That's why I did this part, V2 equals V3. And then that gives you I2 R2 equals I3 R3. And then that allows you to solve for just one of the currents, for instance. And then when you saw that R3 and R2 are equal, that's what allows you to conclude that I2 is equal to I3.
Okay.
Okay. How about you, Mark? You have any questions on that one?
No, I think I got it now.
Okay. You sent me another one. You want me, which number are you looking at now? Anybody else has another question, we can interrupt it, but I'm in the middle of a question that Mark offered. If anybody has one other, I'll do that.
It's question 10, all
Question
the
10.
last picture.
Yeah, I found some problems with some of these. So this says a a rigid rectangular loop. Is that the question 10 you were talking about?
It's a wire in the shape of a M.
Oh, okay, gotcha. I'm gonna check. Ah, there it is. Okay. A wire in the shape of an M lies in the plane of the paper. It carries a current of 2 amps flowing from A to E as shown in the figure. It is placed in a uniform magnetic field of 0.65 Tesla in the same plane, directed as shown on the right side of the figure. Okay. The figure indicates the dimensions of the wire. Note AB is parallel to DE, and the baseline from which the magnetic field direction is measured. Note AB is parallel to DE and to the baseline from which the magnetic field direction is measured. Gotcha. What are the magnitude and direction of the force acting on section BC of the wire? Okay, so that means I need to draw this real quick. So let me flip to another page, and I'm going to draw this M. So the M looks sort of like this. I don't know why I'm doing it in red, but that's what we're doing. And then it comes to here, and then it comes to here. Oops, not there. Comes to there, and then it comes back to here, like so. And this is A, and this is B, and these refer to points. And this is C, and this is D, and this is E, and AB and this is what you write mathematically to show that 3 lines are parallel, or in the case of 2 lines, it would just be the A, B, E, D are parallel without that bottom diagram. What I'm doing is including this other guy, which basically says this is the direction of the magnetic field, and this is F, and this is G, like that. And this is 45 degrees. This is 40, well, actually, let me not write it there. This is 45 degrees. You probably all can tell that the angle at C is actually 90 degrees. This one's 45 degrees as well. And like I said, they want to know uh, what are the magnitude and direction of the force acting on BC. So, what is F total on BC? In the math world, if you take 2 points, B and C, for instance, and you draw a line over them, then that just means a line segment from B to C. And in fact, it doesn't even say necessarily from B to C or C to B unless you put an arrow on it. In this case, I do have to include the arrow because the currents through this wire are going this way. And the current, they said, was I equals 2.0 amps. And the magnetic field B, oh, I forgot a question mark there. The magnetic field B has a magnitude of equal to 0.65 Tesla. And again, what are magnitude and direction of force acting on section BC of the wire? So section BC of the wire, really, because it's at this particular angle, the magnetic field that exists uh, can't really do much of anything on the force because the solution right here gives us our equations, and our equations are such that F is equal to, well, actually, I shouldn't put a vector symbol on that because I'm in my 202 class. So F is equal to I times L times B times the sine of theta. So I need the length of the wire, the current going through the wire, and the magnetic field strength. We have all that, even though I didn't necessarily draw it. So let me now go back and draw that this is 10 centimeters. This is 6 centimeters. Oops. Okay. This also is 6 centimeters. And then this one down here is also 10 centimeters. All of which I'm assuming are 2 sig figs. So we have all that. Now, what I want to point out is what we're really looking at here from a vector standpoint is we have our thumb, then we have our index finger, so something like this, and then we have our middle finger, which is going through there like that, and then we have our ring finger, and then our pinky. And that last part didn't turn out quite as well as I had hoped, but that's pretty good right there. Okay, and again, what we say in this case, this vector is either I times L or Q times V. This vector is B every time. And then this vector, get a different color. This vector is F. So that's our right hand rule. And in fact, if you want to be very precise about it, you'd realize that this has to be a right angle with that, and that middle finger is actually in a whole different plane than the green and the red vector. So it's also perpendicular to it because it can't reach straight parallel to B, so that would keep it out of the plane, nor can it reach straight anti-parallel to B, so it can't reach out of the plane there either. So B is in some sense perpendicular to A and to, or excuse me, to IL or QV and to F. All right. So if I'm looking at segment BC, which is what we're looking at, we have a IL that literally points from B to C. So from the figure, whoa, from the figure, the current suggests that IL points from B, from B, the point, to C. Uh, that vector is anti-parallel to B, so F equals I L B sine theta equals I L B sine 180 degrees, which equals zero. That's the whole force due to just the magnetic field. Now, there may be a magnetic field at BC that's due to the current. And if that's the case, then yeah, you could actually have forces on it. It might not be very big, but it would have forces. So now I'm checking that right quick. What are the answer choices on this particular one, I wonder? That's not it. Sorry. I'm checking back the questions that he sent me. Point 0.090. So they're using consistently the numbers 0.06 or 0.09. I suspect if you take the 20 amps and or the 2 amps, excuse me, and multiply it by the 6, so 2 times 6 times 0.65, that gives me the 7.8. Well, that's not helpful at all. Oh, and then you do sine 45. That gives me about no, that gives me about 5. That's weird. Okay, so it's not that. I'm just trying to look and see if where they came up with that figure. So they did say 0.65 times this times 0.06. That's what it is. 0.06 times 2 times 0.65 is 0.078. And then if I multiply that by that gives me 0.06. Okay, and if I multiply it by cosine of 45, that get duh, I knew that. I knew both of those were 45. Okay, so as best I can tell, this answer should be zero. I don't see any way that we're going to get that much of a magnetic field on the line segment CB as a result of the magnetic field from CD, the magnetic field from DE, and the magnetic field from AB. So I'm thinking the answer is supposed to be zero. I will double check that just to make sure, but I don't see any way it could be 0.06 or 0.09. So that's probably fairly reasonable. Let me get over here to the appropriate course, which is what I'm in now. And I'm going to go to quizzes and I'm going to check that. You said this came out of a practice test, Mark?
Yep.
Which practice test was it? Do you recall?
1621.
Gotcha. 16 to 21.
I have seen a similar question to that, but the magnetic field that it provided was 0.85.
Uh-huh.
And I think I asked you about this before weeks ago because I was confused on why was it not perpendicular out of the page instead of in the page. And just to be clear, because they have the magnetic field going on that, basically going up, which I'm assuming what B is, right?
Uh-huh.
And that like short diagram where it has a 45-degree angle. So if you were to use the right hand rule, you wouldn't try to put your middle finger kind of going in that direction to kind of figure out where the force is? Like, would that
Uh,
even work? Like, is that because I think my confusion was like, okay, well, since I see B going in that direction, that's probably where I should try to like picture my magnetic field going, right?
right.
And when I do that, I guess I can say I can see it pointing into the page, right?
Gotcha.
I don't
Uh,
know if it's making sense or not.
Yeah, I did check this one, by the way. I'm having a hard time understanding some of the wording you're using, and it's not necessarily anything wrong with it. It's just the way you're saying the way the magnetic field is going. Uh, I would normally say the magnetic field points in a certain direction, but I'm wondering, are you picturing a moving magnetic field, or am I just mishearing you?
So like, okay, so 2D version, you could see that it says B has the vector over it, like the diagram that shows B,
Hmm.
which I'm assuming represents the magnetic field, right?
Right.
And then so when so me looking at that, I use the right hand rule, and the index finger in the right hand rule is the magnetic field, correct? So when I
Yes. Yes, that's right.
So when I try to use my index fingers to point in the direction of where like the 2D version of the page is pointing, which is
Uh-huh.
kind of 35-degree angle, I do realize that my thumb, which is the force, correct,
Right.
is pointing into the page, right? So I'm just basically asking, is that like
Oh, okay. I
a
see what you're saying.
reliable?
S-
Yeah, is that like, because
So,
like I can't vision 2D version, the hand that you just drew, like that would not tell me that your thumb is pointing into the page at all.
right.
You
So,
know?
what's going on here is you're saying you're wanting your index finger to point like this,
Right.
which is
And like
parallel to
kind
the
of how
magnetic
the
field.
indie, right. And
And
then,
but the problem is the middle finger can't be exactly parallel to that. If it's exactly parallel, you automatically get zero. So if your fingers are literally like this next to each
mm-mm.
other, see how they're
Yeah.
0 degrees? If they're just slightly off like that, then that's a non-zero result. But anything where they're parallel or anti-parallel, which would be like this,
Mhm.
anything like that's automatically going to give you zero. And not only that, it doesn't well define a direction because all of these I'm still parallel to the magnetic field and to the current carrying wire. So all those force directions are possible. So it
So
only
I
works
don't,
when that middle finger
yeah.
has to be at some angle to the index finger.
Yeah, like perpendicular, like at a 90-degree
Yeah,
angles.
yeah,
I do get that much because when I did that, I do realize that like it looks like it's insinuating that the force is actually down pointing towards the page.
right,
Or at least because I'm going off the fact that my thumb is representing the force.
right.
So that's all I'm saying. Like,
Gotcha.
because I'm trying to find a reliable way to use this.
Yeah. So what I always do is I imagine this little index finger, imagine it like it's one straight bone or axle, if you will, and
Mhm.
then welded to it is another straight bone that's perpendicular to that first one, and that makes my thumb.
Mhm.
When you do that, then you can't rotate this finger without the thumb coming with it,
Right.
but you also can't rotate that finger without the magnetic field, the middle finger going with it. But that middle finger, I can't weld that one because that has to be able to go all the way to, 1 degree and all the way up to 179 degrees. Uh,
Okay.
Ideally, you'd want it 90, but it's not always going to be that. So
Right.
when you're thinking about it that way, then all you have to do is make sure that one axle of the index finger is parallel to either the QV or the IL, which in this case would point this way for this one because the IL, the current is going down and to the left, not up and to the right. So it
Right.
would be this way. And once you have that, if you don't know the magnetic field or the force, then all these directions are fair.
Okay.
But once you nail down, let's say the force is this way, then the magnetic field has to be somewhere between or between 1 degree and 179 degrees, like this.
Okay.
But that's once you tied the force down. In this case, we actually had that the uh, IL is this way, but the B is actually exactly the opposite. So I'd have to actually do the 180 degree. And when I do the 180 degree, I know the answer is zero. I will tell you, I looked this up, Mark. The answer I would actually argue that both of these are potentially correct. If you're ignoring the effects that the other wires cause on the segment CB, then the correct answer is zero, and that's what's listed in the bank as the right answer. But there's another answer that says none of the above, and I would not necessarily say that's wrong because I'm almost 100% sure that if you add up the contributions from the segment AB, the segment CD, and the segment DE, you are not going to get zero point zero 0.09 or zero point zero 0.06. You're going to get a much smaller one. So this would just not make it to the final period. No ifs, ands, or buts about it. In fact, I'm probably going to have to completely revamp that to some extent because I'm finding a lot of issues with it. And in fact, I've already found a lot of issues because I got 6 versions of it in the bank, and some of them are called fixed and some of them are not called fixed. So that means I've been typing in there and fixing them.
Okay.
So
Um,
don't worry about this one, Mark. But in this case, I would say zero is probably a good answer. But I'd also would have accepted none of the above just because of those complications.
hey, I have a quick question that help me with the understanding of the electrons and protons with the magnetic field. So
Uh,
protons go in the same direction of the magnetic field, correct?
I missed the first part. You said, what's the same direction of the magnetic field?
A proton, it goes in the same direction of it.
Oh, okay. Yeah, that's a little misleading, but I think you're on to something that's right. It's just a matter of the wording's not quite there. Uh, in no case necessarily does a magnetic field compel a positive particle to move parallel to it. Period. That just can't happen. But it can make it move perpendicular to it, and that's the normal thing. Okay.
Okay. And then they say because there was a conceptual question that you had,
Hmm.
like one of the practice questions. I'll try to hunt it down for you, but when I was practicing, it was asking like a scenario of like which direction would a proton or electron move with the magnetic field. And I believe it insinuated that electron would go like oppose the magnetic field, and then a proton would move in the same direction of it. So there was a conceptual question that kind of insinuated that.
Oh, I think that's with regards to Faraday's law and Lenz's law.
Okay.
Because that sounds like they might be talking about conventional current, which is the directions that protons would travel, and real current, which is the direction that electrons travel. Because we know in reality, it's not really like a positive side of a battery compelling these protons to run around and come back in the negative side. In
Yeah.
reality, it's the negative side of the battery compelling these electrons to move around towards the positive side of the battery. In that case, then yeah, you're going to find some words, but it could literally go exactly the opposite in a slightly different problem. So I would
Okay.
not hold on to that memory that protons go in
Okay.
the direction of the magnetic field and electrons go in the opposite. I wouldn't hold on to that because there's a lot of instances where it does exactly the opposite.
Okay, cool. Because
Okay.
yeah, I was looking at a question. Actually, it was one of the questions on the test, number 17, the first test, when it
Uh huh.
talked about a proton is placed in an electric field of intensity 800. What are the magnitude and direction of the acceleration of the proton due to this field? And then, I mean, I got that one right. And then it was in the field of the electron. It was in the direction of the electron field. I knew that based off of the fact that protons moved in the same direction of the electron field and not in the opposite. So you say
Gotcha. So you said what number was that? I'm pulling that question up so we'll have exactly the right wording.
it was
Question seven?
question 17 in the
17.
first
Yeah.
test.
Okay, I'm looking at that right now. It says a proton is placed in an electric field of intensity 800 newtons per coulomb. What are the magnitude and direction of the proton, acceleration of the proton due to this field? Okay, so in that case, you have an electric field, which electric field does a lot weirder stuff than or a lot more normal stuff than the magnetic field. The
Okay.
force on a charged particle in an electric field, let me write it down here so you'll know. the force on a charged particle due to electric field is just F is equal to Q times E, and that is a vector equation. So what that means is positive particles do travel, and this might have been what you were thinking of, but you were thinking we were talking about magnetic fields. You were saying something that's true, but about electric fields, not about magnetic fields. So
Okay.
positive particles do travel in the direction of the electric field.
Can you go
Okay.
over that problem? Can you work it out?
Yeah, we'll do in the direction of E field. And electrons, negative particles, do the opposite,
Okay. Yeah. Okay, I can see it.
the opposite way. So let me go ahead now and address this problem. I've got it pulled up. Did y'all get that information? Because F equals QE, remember when you multiply a vector by a negative number, you just change the direction. So if the electric field was pointing to the right and you multiply it by a negative number, it's now going to have a force that points to the left. And if the charge is positive, if the electric field points to the right, then the force is going to be to the right. So let me go ahead now and say this question. It says a proton is placed in an electric field, E equals 800 newtons per coulomb. Later we'll learn that that's equivalent. Well, we've already learned it, but remember you can also use volts per meter. So the electric field is 800 newtons per coulomb. What are the magnitude and direction of the acceleration of the proton due to this field? So we want to know the acceleration, and I'm going to put a vector symbol over that because they want to know the magnitude and direction of the electric field, I mean of the acceleration for a proton. I do know that the charge of a proton, Q sub P, is actually the letter E, which is positive 1.60 times 10 to the negative 19th coulombs. I also happen to know that the mass of the proton is 1.67 times 10 to the negative 27th kilograms. But your book also gives you both E and, or I say your book, the test question actually gives you both E and the mass. So what we're going to do here is we're going to say F in magnitude is equal to Q times E. So we can do that, and we're also going to say
F equals MA.
exactly F equals QE, and F, the summation of the forces from Newton's second law, is equal to mass times acceleration, assuming the mass doesn't change, but we're not worried about that. So this is all basically one-dimensional motion. So I'm going to say that the force is something we can calculate. I'm going to do that first. So F is equal to 1.60 times 10 to the negative 19th coulombs times 800 newtons per coulomb, which gives me, really need my glasses, 800 times 1.6 times 10 to the negative 19th gives me 1.28 times 10 to the negative 16th newtons. Okay, and that's one extra sig fig at least. So that's the force. Now we're going to say the summation forces in that particular direction, which is the direction of the E field, is equal to the mass times the acceleration. So the acceleration is going to equal the force divided by the mass. So I'm going to take the 1.28 times 10 to the negative 16th newtons, and I'm going to divide that by 1.67. And who writes their 6 that way other than me? I don't know. Times 10 to the negative 27 kilograms. And I'm going to take this 1.28 times 10 to the negative 16th, and I'm going to divide it by 1.67 times 10 to the negative 27th. and you're going to see that it's going to get a rather large acceleration, 7.66 times 10 to the 55. And that unit is a Newton per kilogram. Remember, 1 Newton is defined to be a kilogram meter per second squared. So if I divide a kilogram by that, I just get a meter per second every second is equal to the acceleration. And that's the magnitude. And since it's a positive particle, the direction is parallel to E. So
That
parallel to the.
is none of the answer choices. 55 is way too big. They're
Yeah,
all
that's crazy.
10 and 9s.
Wow, that was way
The
out in
power
left
of 10 and
field.
9.
Yeah, I'm looking at the
Yeah.
answers right now. Proton is placed in an electric field of intensity 800 newtons per coulomb. What are the magnitude and direction acceleration of the proton due to this field? Yeah, that's just a bad question. And now I got to find that one. But it did have the 7.66. That made me feel a little better. Uh, Let me check my math.
I
I
was
don't
gonna
see
say
anything that
because when
went
I
wrong.
plugged it into the calculator, I got times 10 power. Let me see, because I think it was correct, but you just put
Yeah, I
50.
got the answer correct. I just need to find out people.
1.28 e to
Oh, wait a
the
second.
I
I
think you just messed
divide
up on your
that by.
calculation. Where did I put that?
Yeah, I
Hold on.
just
This.
think you got
Ah,
50.
there you go. That is good. It's 10 to the 10th is right. I don't know. I think I'm. Hmm. Oh, I can see it now. I
you
hit
have
the negative button twice, evidently. I
and that
divided,
would
yeah,
be
the exponent of 10 to the negative 27th. I hit the button twice, I think, because this time I did it and I got the right answer. Oh,
so
no, it's worse. I did.
Yeah,
I
I got.
totally went dyslexic. I typed a negative 72. So it is 10. Thank you for checking that, everybody. That's awesome. That's
Yeah.
exactly what you're supposed to do. That's exactly what I'm not supposed to do, by the way, but still. And I'm glad y'all were paying enough attention. I hopefully would have been had I not been in teacher mode. But yeah, 7.66 times 10 to the 10th meters per second, parallel to the electric field, is the right answer. Thanks, Brittany and Mark, for both of y'all getting the right answer, and for Kyle pointing it out. Yeah, I had literally typed negative 72. For the exponent. That seems perfectly reasonable to me. I don't know why y'all.
it's in the direction of the electric field.
Yeah, it is. It should be parallel to the electric field because it's a positive particle.
So I just had an epiphany.
Yes, ma'am.
Now that you help clear it up, like the understanding I have for magnetic field and the electric field, I get that they're two different things. So for the magnetic field, it's best for me to think in along the lines of clockwise rotations and counterclockwise rotations to determine like a projection of a particle and electron, correct? So
In some sense, yeah, because that's really how you have to sort of think of the magnetic field is it's always curling around something.
right,
So that's
exactly.
reasonable for you to think that way.
So back to question 17 we went over earlier regarding that proton moving west and why it's rotating in the direction of the south, because I'm trying to figure out how I can explain this and on the redo test. I
Hmm.
was going to say, well, being that the proton is entering west and it curved upward, that's because the magnetic field is in a direction in a clockwise rotation. And that also explains why the magnetic field will be pointing south then towards the south, right? Because that's
Ah,
the so is that like a good way to like very simple, good way to kind of clarify my understanding?
sort of is, but in order for something going to the west to
Mhm.
have a feeling going up, this is very weird now. QV going to the west,
Mhm.
causing a force up, has to be represented by a magnetic field coming out of, coming south, basically. So if the magnetic field was headed towards my nose from the screen of my computer, that's due south. If the positive particle was traveling due west, that's to my left, then it would feel a force going up. But when you think of that magnetic field is just a bunch of lines coming at me, like shooting at me, but it's causing things to rotate this way. So your idea of thinking about rotations or revolutions around things is good, but it's weird because you're missing just one little bit. The magnetic field isn't curled around the velocity of the proton. It's more like the projectile of the proton is going to curl around the magnetic field lines
Oh, okay. I see what you mean. So the magnetic field, like you said, is basically straight,
for
straight,
that one. Yeah.
right. Okay. So if it's coming like out, which it will be coming out towards me with the proton moving west, now I'm just having to envision a proton orbiting around this field. But okay, so then I guess that's not really gonna help.
Yeah, your idea is really good. It's exactly what Maxwell came up with, to be honest with you. Maxwell envisioned sort of like a wheel like this with another wheel wrapping through the inside of it. And
Uh-huh.
what he represented was sort of like the magnetic field was the wheel wrapping through the other wheel, and the
Right.
other wheel was like the trajectory. It's just really hard to work that out. So yeah, you're on a really good thought process, but I wouldn't put as much time and effort into it as you need to, because that's more or less a nice mechanical way, but I don't think you'll get there before the end of the semester because it took Maxwell some time to figure that out, you know.
Yeah, I'm just trying to get whatever
But you
is
did
gonna
it.
give me an
Yeah,
A.
exactly. So yeah, just remember that so that velocity going this way, check this out. If it had a component that was south, so the velocity wasn't directly west, but maybe just a couple degrees south of west, then what would happen is that component of velocity that's pure west is going to make the thing go in a circle, 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 circle forever. But the cool part is if it has a velocity that's a little bit south, then what it's going to do is it's going to make a circle while it's also going south. So it's going to spiral around and around and around like this. So that's what would actually happen with it. And if those types of pictures are helpful to you, then by all means think of them. But like I said, it is not a trivial task to make up the actual processes that this goes through. May I help you? Hey, baby. Thank you. Love you, baby. My wife's gone to get lunch for us. So does that help you any, Brittany? Or if it makes it worse, just throw it away.
Okay. I think I'm definitely gonna need some practicing to really visualize this so that way as I encounter these type of tests is like because I see that my understanding clearly was enough to get me the correct answer. I'm just worried that maybe
Exactly.
I'm gonna throw something else different in there and then now I'm kind of gonna be relying on something that's not gonna
Ah, well, that's the good thing. No, I can't throw anything different in there because you have access to virtually all the questions I could possibly do. So the more you're doing these practice tests or stuff like that, the more you are seeing the actual questions that could appear.
Okay, so are you gonna stay true to what we seen on test one and two as far as the concepts and the type of problems? Like we're not gonna like expect the because I know you had one question up there where we had to like find the magnetic field of a particular corner inside of a question that was like very, very long to like figure out. And but that was not on a test, thank God. It was just like a
Yeah.
practice test
Yeah,
that
my guarantee in my class is that 80%, at least 80% of all the points on the final exam will
Mhm.
come from those previous tests.
Okay, great. All right.
So, and to be honest with you, in 10 years, it's always been 90% to 100%. I think I've maybe one time in decades, I've changed it and taken something that was new, literally maybe one or two times in 30 years.
Okay, well that's good to know because I actually, since I've been practicing these past two tests, I feel better. I see where I messed up. I see where I was confused. So I think I'm really getting a lot of these concepts, at least on a like mathematic level. So it shouldn't be as bad as I'm like, so I feel a lot better about that as long as it stay true to that, but
Yeah, yeah, exactly. No, and you it will be. So yeah, you're on fire. What I would recommend you do just to make sure you're comfortable with what's going on is
Mhm.
chapter 20 is where we handled all that. So
Right.
I would go into my Canvas page and click on modules, and you'll see there's chapter practice.
Right. I've been doing that. I have.
And I would just do the first one because the other ones are actually computational. If you want to do them, that's fine. But what
Okay.
you're wanting to practice on is getting your directions right, which should be the first question in chapter 20 practice. Because the way
Okay.
I've got it set up is the first question is a concept question, and the
Mhm.
next three are problems. So if you just
Okay.
did the first question, you'd literally only be addressing concepts. The grades don't go anywhere. It's just you getting to do it over and over and over again. So I just say jump into chapter 20 and do, 100 of those until you consistently get it right. And then you'll not only have you'll probably have seen all of them, but you'll also have more or less worked out all the kinks of your system of trying to make it simpler for you.
Okay. And now as far as 21, that was a chapter we didn't spend too much time on. Is it going to be heavy in that? Do I really
No,
need to
it should
worry
be much
about?
lighter in 21. Chapter
Okay.
20 is way more focused. And
Okay.
what I did with the practice test is I sort of just went through and picked the bare minimum of what I expected of you of chapter 21, and I put
Mhm.
that in the practice final.
Is that mainly conceptual or should I focus on the algebraic techniques of that too?
There is a little bit of algebraic techniques. There's some simple use of the formula EMF equals B times L times V. And there's the simple transformer equation, which is V primary, or excuse me, V secondary over V primary is equal to N secondary over N primary. And then the other one for current, which is both of which are on your sheet. But that's pretty much it. And the vast majority of those questions are conceptual.
Okay. Can you write down those formulas so I can highlight them on my sheet?
Yeah, I'll do that.
Thank you.
There was one that was E is equal to B times L times V. And that was specifically like when we had a rod moving through a magnetic field, say, like this, where this length right here is L and it's moving with a velocity V. And this magnetic field is what I'm drawing in those little purple circles. That's one of them. The other one is V secondary over V primary is equal to N secondary over N primary, and the I secondary over I primary is equal to, notice the difference here, N primary over N secondary.
Okay. So these are chapter 21. All right.
And remember, words like step up means voltage goes up. So step up transformer implies V primary is less than V secondary. And of course, that implies N secondary is greater than N primary. And just for a picture of that, you can imagine the old Thanksgiving play that you had to do every year, like in second grade or whatever. There's the belt buckle from the Pilgrims. And this one has N primary turn, or excuse me, secondary terms. Why did I write P there? This side has N secondary terms, and this side has N primary turns, and this voltage is V primary, and this voltage is V secondary.
Okay.
So that's what the NS and the MP means is the number of turns you have around that hunk of steel or iron.
Okay.
And that's really what a transformer is. The power companies have figured out using a lot of science and experiment the best ways to do so efficiently. So these belt buckles are more or less plates of steel that are glued together and often submerged in some really carcinogenic liquids and oils and stuff. But the main premise is right, and it still works to do that. You're just not going to get 100% efficiency if you just did it with an iron belt buckle.
Okay.
You're never going to get 100%, but you're not even going to get close to 95%, I bet, with that.
Okay. I'll
I
definitely
have
review that.
Gotcha.
I have
What
two
was
more
that, Kyle?
questions. Yeah,
Was that?
yeah, I have two more questions. So the
Go for it.
one is test one. It's the
You're talking
it's
about
the
the
one that's a
face-to-face
graph.
test one, right?
Yeah, it's a
Okay.
graph and it has a 45-degree angle and its current is on the y-axis and potential is on the x-axis. And what quantities does the slope of the graph represent for a ohmic material?
Okay. I'm going to look for that one.
I think it's
Graph current on the vertical and potential on the horizontal.
yeah, and if
Okay, yep.
the y equals mx plus b is on it's like a 45-degree.
Yeah. So it looks, I think I found the one. It says current and it says potential and it has a line like this and it's asking what physical quantity does the slope represent? So
Yeah,
slope equals question mark. So if we look, there's an equation called Ohm's law that says V is equal to I times R. So if you were to try to graph this, then you might say Y is equal to uh, X times R. And that means if you graphed potential on the vertical axis and current on the horizontal axis, then the slope would equal R. Okay, but we don't have that. We have current on the vertical axis. So what you need to do with this one is you could say I, since that's on the vertical axis, is equal to 1 over R times V. And then you'd say Y equals MX. And then you'd see that the slope in this case is equal to 1 over the resistance. So that's a
okay.
skill. I know I've been trying to teach that the whole semester with in your lab, but I would venture to say 90% of the students haven't quite put it together yet because they're still asking me questions like it. And that's not just my 202 class. That's my 241, my 242 class. I still got a good fraction of students not getting that. But in general, what you always try to do is say y equals mx plus b if you see a linear equation and then you realize that the vertical axis is the one that's solved for, and the horizontal axis is the what we would normally call the independent variable. So all you have to do with any equation is solve for the variable that's on the y-axis and then see what you get. That's what I did right here when I solved V equals IR for a current. And in so doing, that showed me that x being this means the number in front of the x had to be the slope. So that's why the slope became 1 over r.
Okay.
Does that help you, Kyle?
Yeah, I think I got that.
And
Um,
when they go through the origin, that just means the b is 0. So that's why you don't have to say plus something.
the next one was test two. It's a three-part problem. It's
Okay.
the question 10, 11, 12. At least it is for me.
Okay. Yeah, that's the way I did it. Yep. So
It's
this
the
was
current.
face-to-face test 2. I
Yeah,
think I know which one you were. It's like one circuit problem that you had to work over and over again.
yeah,
So was it problem the 7 ohm, 8 ohm, 4 ohm, 12 volt, and 9 volt?
yes.
Okay. Let me go ahead. Whoa, Nelly. I just I changed the screen on my iPad by accident and didn't realize it, but y'all didn't see it, so it's fine. So here's the circuit we have. Uh, I'm going to put it on marking color that's decent. So what I have is a wire running into a 12 volt battery, and then that 12 volt battery runs into a junction, and then that junction has a 4 ohm resistor like this. And I'm going to treat all these like they have 2 sig figs. It also has up here a 7 ohm resistor. It also has over here a 9-volt battery and an 8 ohm resistor like this. And what they want is part A, which is really the first one. They're wanting I7. That means the current through the 7 ohm resistor. Part B, which is really the next question, they're wanting I8, which is the current through the 8 ohm resistor. And then part C, they're wanting I4, and that's the current through the 4 ohm resistor. So notice they didn't draw any directions on here. That's very normal. I want you guys to understand you have to choose what direction you think the currents are going. So what I'm going to do is I'm going to assume that this current leaving the battery, this is what we're going to call I7. And then from that is a current I4 leaving that junction. So here's our junction right there. And then we have, I'm going to say I8 goes this way as well. So solution.
Can we submit this to all three? Since we're just doing A, B, C.
Well, oh yeah, I'm just going to work the whole problem.
Yeah.
Yeah,
But I mean,
that's
like, as far as on the redo, can we just put this picture for all three?
oh yeah, absolutely. Yeah, it would be nice. That would be normally the way I'd like to do a circuit problem in the actual test and stuff like that. As far as this goes, yeah, you can just put all of them 1, 2, 3, and then just put one big solution at the bottom. That'd be fine. So Kirchhoff's junction rule. That says the sum of the currents in is equal to the sum of the currents out. If I look at the purple junction, I've got exactly one that comes in, so that's I7. And I've got 2 that comes out, so that's I4 plus I8. So I'm going to call that equation 1, like that. And then I'm going to do Kirchhoff's loop rule. And this one's going to be for the left loop. So for the left loop, I'm going to start at the junction and go counterclockwise. So start at purple dot, or excuse me, at and traverse counterclockwise. So I'm going around that left loop counterclockwise. That happens to be with, in other words, I'm going the same direction as I4 and the same direction as I7. So that's critical because I don't know why I wrote a Z there. That's critical because when you go the direction of a current, then your resistors are voltage drops. So now I'm going to go ahead and write minus 4I4 minus 7I7 plus, now notice I'm going from the short leg of the battery to the long leg, so that's a voltage increase, so I'll say plus 12, and now I'm back to the junction, so I say that's equal to 0, and I'm going to call that equation 2, and now I'm going to say Kirchhoff's loop rule, and this time I'm going to say outer loop. And I'm going to say start at the purple dot again and traverse counterclockwise. In that case, that means with I8, but counter to I4. Okay, so when I do that, I'm going to say plus 9 because I went from the short leg of the battery to the long leg of the battery. And then I'm going to go minus 8 I8. And then I'm going to go plus 4 I4. And then I'm back where I started from, so I'm going to say that's equal to 0, and I'm going to call that equation 3. I've got 3 unknowns, 3 equations. That's exactly the way we like it. So what I notice is both equation 2 and equation 3 have I4 in it, so I should solve for the other current in each case and then plug them in one. So both with an E on the end, both 2 and 3 have I4, so I will solve for the other current in terms of I4. So 2 is going to imply, for instance, I7 would be, I'd have 7 I7 on the other side, so that would give me I7 equals 12 minus 4 I4, and then I divide the whole thing by 7. And what I've enjoyed doing is just making this into 2 separate numbers with decimals, because that's sort of the easiest way to work it with my calculator. So I'm going to take 12 and divide it by 7 and hope I don't screw up my fingers. I'm going to call that 1.714 minus, now 4 divided by 7, that's going to be 0.5714 I4. And this is equal to I7, and this is equation 2 prime. Now 3 is going to give me I8, and I8 is going to become 9 plus 4 I4 over 8. So 9 divided by 8 would be 1.125, I think. 1.125 plus 4 divided by 8 is 0.5 I4. So this is equal to I8, and this is going to be called 3 prime. Now I plug 2 prime and 3 prime into 1. And when I do that, I get I7 is equal to I4 plus I8. So I'm first going to write I7, which is 1.714 minus 0.5714 I4. Now that's I7, and that's supposed to be equal to I4, which is what we've been solving in terms of, plus it's supposed to be I8, and I8 we said was 1.125 plus 0.5. Notice if there was a minus after the I4, I'd have to distribute that, and I'm technically distributing the positive too, but the main thing is since it's positive, it don't matter. So it's 0.5 I4, like that. So now you see we have exactly one unknown, and it looks like if I pull all the I4s on the right, then I would get a positive coefficient of I4, and that makes me happy. So I'm going to say 1 plus 0.5, that's obviously 1.5, plus 0.5714. That's going to give me 2.0714 I4. And then on the left-hand side, I got 1.714, and I'm going to subtract from that 1.125, and that's it. So the left-hand side becomes 0.5890. So this tells me that I4 is equal to 0.589 divided by 2.0714. And that's giving me 0.2843 amps. Now, we're probably supposed to just be 2 sig figs, so I'm going to assume that we could just cut that off. That's not necessarily accurate, by the way. You need to really trace these dots out and see where the sig figs come out to, but we'll just go with it for right now. But now the advantage of doing it this way is we've already got it solved for I7 and I4, so now all I have to do is say I7 is equal to 1.714 minus 0.5714 times 0.2843. So I'm going to take the 0.2843 and multiply it by 0.5714. And then I'm going to say 1.714 minus that number, which is 1.714 minus 0.1624. And that gives me I7 is equal to 1.552 amps. So that's I7. Again, probably without the last 2 digits. And then I8, that one's supposed to be 1.125 plus 0.500 times I4, which is 0.2843. That gives me I8 is equal to 1.125 plus 0.5 times 0.2843 gives me 1.267 amps, and that should be I8. So I'm looking at 1.5, 1.3, and 0.28. Let's check our answers. It appears to me that I7 is 1.6. Yeah, that's accurate. I misstated. That 5 should cause us to call that 1.6. So that one's correct. Check. Then if I look at the next one, it's asking for I8, and I8 is 1.3. And actually, I misrounded on that one too. That should be 1.3. And the other one, which was I4, we think that's supposed to be 0.28, and that's exactly what they have is 0.28. So, any questions on that one, Kyle or Mark or Brittany?
So I I got my answer a totally different way, but now I see why it was off because
Oh,
the way I went about doing it was like um I kind of like just got the answer and the closest value is what I went with. So like
gotcha.
it's like the first one, for example, for finding seven.
Mm-hmm.
I went with the equivalent equation. Like first I put 7 and 8 as a series, and
Ooh.
then I did that as I'm not a series, as a parallel
Mm-hmm.
equation. And then I used the series equation for that answer to get it all together, like the entire total of the resistors in the circuit. And then I divided that by the voltage, which was 12, and that got me the 1.55, right?
Wow, crazy. Okay. That
Right.
seems to
So,
be luck. That doesn't seem to be necessarily reasonable, but yeah, that's cool that it got that.
well, all of it added up, and I got that wrong, right? But then when I had to do it for number eight, I mean number 11, for the eight resistor, that's when the breakdown began for me because it
Gotcha.
was like I wasn't really getting the answer like close to it. So the closest value I got for number 11 was 1.16. I was like, okay, well, what's the closest one of that? And I went with 1.3.
There you go.
And then the same thing for 12. So I kind of appreciate this because I was wondering why were my answers off? They were pretty off, but they were close enough for me to like know which you like
Right.
clearly the closest value.
Yeah. Well, this is the way that there's actually a couple different ways you can do it. Sort of something like what you were doing. There is a way in principle you could do it like that.
Mhm.
At least with more complicated ones, it'd be really hard to do it the way you did it with this one because there's not enough series and parallel resistors all on the same leg of a circuit. But
Okay.
there are a bunch of ways. But the way I taught is just you have Kirchhoff's junction rule, which says you take all the currents that enter a dot. Remember, a junction or a dot is a place where three or more wires come together. Once you choose the directions of the currents and the names of the currents on those legs, then you take all the ones that are entering the junction and add them up, and then you take all the currents that are leaving the junction and add those up and set them equal to each other. That's Kirchhoff's junction rule. And then Kirchhoff's loop rule says that if you go around any closed loop in a circuit, the sum of the voltage increases and drops will be zero. So that's the way I was doing that. But the caveat with that is that if you're going on a particular leg of the circuit, if you're going the same direction as the current, then the resistance will be a voltage drop. But if you're going the opposite way, the resistance will be a voltage increase. And of course, batteries always increase when you go from the short leg to the long leg and decrease when you go from the long arm to the short arm. But
Mhm.
other than that, that's basically it.
Okay. So I'm
Okay.
gonna have to definitely practice this way because it's definitely I did because of the way I did it, I didn't have to do so much of the math and breakdown. But
Right.
like I said, my values were like my total was off. It wasn't off enough for me not to get the right answer, like close to the right answer, but it was off. So I will definitely try to look into that. And like, okay, and as far as the circuit go, you said the long bar, that's like basically the positive, right? Where it starts and
Exactly.
then the shorter one. Okay.
Exactly. Uh, so it's plus minus like that. So I
Okay.
just wrote in red, search for Kirchhoff on my YouTube channel, and you'll find 1,000 of these examples where I'm solving circuits that way, so you can get plenty of experience just watching them. And don't feel obliged to watch the whole video. Just fast forward until you get to somewhere where I'm drawing one of these circuits, and then watch me. And that's all you need to do to prep for that. Mason just came in, but I'm getting ready to have to kill it. It's time for me to go eat. My wife just brought back everything, but let me ask Mason, do you have a question for me, bud?
Yeah, so the practice test for the final exam, it only let me take it one time. I was wondering if we're only allowed one attempt or
No, definitely not. What class are you in, Mason?
241.
This is a 241 class. Okay, I'm going to fix that. I'm glad you let me know. I haven't received any email from anybody, but I think that's because people have been working on redoing their test as opposed to doing the practice test. So let me go fix that right now. I really appreciate you letting me know. And you're in
Right.
241, you're my face-to-face class, yes?
Yes.
Gotcha.
Hi, Professor.
Yes, Mark.
For final exam, do we just like, so like you say on Wednesday we can come in at 2 p.m. Do we just like go into class or do we need to like message you?
No, you don't have to let me know or anything. You just show up, and I'll either be at one of our classrooms on that hall or one of our labs on that hall. So you just look for me, and I literally don't know where I'll be until I make the test. So that's why I'm not doing that. That's why I'm not telling you exactly what room to go in, but it'll be on one of those halls. And there it is. I did not click allow multiple attempts. So yeah, that was the problem. I fixed it now, Mason. So hopefully that helps.
Okay. I also had another quick question.
Good for it.
As three dues, we do all questions, including the ones we got right.
Yes.
Okay.
And all the practice. I mean, all the face-to-face tests, not just two of them.
Okay, got it.
All right. All right, guys. Well, I appreciate you all coming. I'm sorry I couldn't stay longer, but I do like the fact that y'all stayed the whole time. But I gotta go eat, and I will have another tomorrow. But thank you for coming.
Have a good day.
You too. Thanks, everybody.